All right, we are back. So we were doing a full series on this AD633 analog multiplier, and we covered a few circuits along the way, but I got busy, very busy. It was a bit stressful along the way. And then I remembered, wasn't I filming a series about this chip and we were implementing circuits? So the basic stuff is over. You can discover the rest of it yourself when you get the chip and the data sheet and the basic developer's kit. But I want to go into the more interesting ones, like the linear amplitude modulator or the voltage controlled low pass and high pass filters. So let us take a look at the linear amplitude modulator, and what that basically is going to be is the same way a microphone will work, for example. So there's this lapel microphone that I use. This is going to be sensitive to my voice, to the air pressure changing. It will convert it into an electrical signal. So that electrical signal needs to be amplified, but we don't want to ruin the quality. That's what a linear amplitude modulator does. It will amplify the sound, but it will maintain its quality. It's the same thing that probably happens when you talk over the phone or over internet protocol. That's what will happen. There is a sort of linear amplitude modulation going on. So this is the circuit we're going to implement, where we have pins 1 and 2 that have the modulation input, and number 3 will put in the carrier input. So let us first talk about modulation input and what carrier input is. Got a blank part of the paper. Let's do this part. So when we talk about modulation, it means to change the shape. It means to change the shape of something. So there's going to be a signal, which will be my voice, for example, and it might look something like this. Okay. I want to send that signal across a large distance wirelessly. I can't. It doesn't have enough energy. So I need a carrier signal. I need a carrier signal that will take this, hold it, and take it to the destination. A professor of mine gave a smart analogy. If you want to throw a piece of tissue paper across the room, you can't. But if you hook it up onto something heavy, like a paper clip or a laundry clip, and you throw it across, you actually can. And when we hook it up, it modulates. So for example, if this is my signal that I want to send, I can't. But if I get a carrier and I hook it up, now I can send it. The fact that these jaws are opening and closing to accommodate themselves to the signal means that there is modulation happening. So the carrier will look something like this, travel over a longer distance. So the modulated signal, the mod sig, will look something, this will have positive and negative parts to it. So the positive and the negative will look something like this. Depending on the two signals that you are putting together and their frequencies. So that's a modulated signal. Since the frequency is changing, since the amplitude is changing, this is what we call amplitude modulation. If I were to do it as a frequency, this is AM. If I wanted to do something else, then I can have something that will remain like this, then it will slow down, get faster, slow down, get faster, slow down, get faster. So you see the difference between those two? This is frequency modulated. It's like when you take a spring and you elongate it. And this is amplitude modulated. So what we're going to be doing in this case is mainly amplitude modulation of a signal with a carrier. So what the datasheet tells us, the carrier input is going to be of the frequency EC carrier, the amplitude of the carrier, omega t, frequency with time. So that's the carrier over here. That's the carrier. And then my signal is going to be the modulation input, which is going to be the signal that I want to modulate. And then we get an output. And this is going to be the formula of the output. But we're going to see it more on the scope in terms of time. Not going to really do any much calculations, but so that you can see how it looks like in real life. The stuff that's traveling across the air every day for us to communicate with each other, how it looks like through the scope and through the circuit. So let's wire it up and take a look at the results. Okay, so we wired up the circuit. Let me give you a more detailed view. That's the chip, and we have two different signals being injected actually. So over here, this is the ADF4351 phase locked loop signal generator, and I'm injecting about 35 megahertz. Remember, I need to stay within the bounds of my oscilloscope, which is 100 megahertz. So this is 35 megahertz, and the oscilloscope is going to be injecting 1 megahertz. So basically up to 30 times larger than the oscilloscope signal. So that's going to be injected into the chip, and what we have is for the modulation input, the signal that, like my voice for example, that's going to come from the oscilloscope, which is 1 megahertz, and the carrier signal is going to be 35 megahertz. So as a result, we will get this. Let's fix this. Yay, the oscilloscope is on low battery. Let's see if we can, I need to hook it up to the charger. I have no other option. Okay, let's just try and make it because I need to fix the adapter. So this is the signal that we are getting as a result of modulation. And let us see. That's how it looks like. And from a distance, you can see the envelope in which the higher frequency signal is versus the lower frequency. And that's how we carry around the signal. That's basically what we are looking for.